So I'm David Christensen, advised by Mark Kukowski here in Stanford, and I'm here to talk to you about my research, microrobots working in a macro world. So we're going to start with the motivation of why we do any of these things and then go through a lot of slides. So for starters here, basically when you look at the world of microrobots, we can break it down into about 4 categories, give or take. So top left here, we have robots made for use within the body. And this is, you could kind of think of it inspired by bacteria or viruses. Some of them explicitly are inspired by such things. But the main idea is when you're within the human body, size is inherently important. You need to be small, otherwise you're harming the human. And so that's a huge motivation for some micro-robotics. Often you'll find that they have infrastructure that's much larger than themselves, because that's okay too. The human can have electromagnets around them or things, but the actuators themselves would be inside the human body and so would want to be size reduced. There's some terrific work by Brad Nelson. There's a microrobot that can swim within the ocular fluid of the eye and then puncture veins and deliver medicines. There's another microrobot that he's developed that can be used inside the heart to perform ablations and all sorts of interesting things. So this is a whole category of robots. We're not going to talk about much today, but they're terrific. The next interesting area that we kind of think about is, okay, so we're outside of the human body. Well, why would we want a small robot? One possibility is to be inspired by cockroaches, so you have rapid and robust ground transport. So cockroaches can get darn near anywhere. They can run really fast. They're really simple in the mind, but they have complex mechanics that make them sort of inherently stable. And that's a really terrific inspiration for roboticists. So there's a whole bunch of actually cockroach-inspired robots. There's iSprawl. There's Ron Fearing Group has Velociroach and a lot of really cool robots there. And so this is a whole category, believe it or not, cockroach microrobots. It's a thing. Yeah, that's right. So the main thing there would be mainly taking a sensor platform and putting it somewhere else. So mapping, exploring. You're not delivering much. They don't carry much payload, but they can move quickly over sort of ambiguous terrain. So that's fantastic. The next sort of interesting area, and this is a new one, not super new, but in the last couple of years, we're seeing bees as sort of the inspiration for flying microrobotics. This is kind of similar to cockroaches in that they're going to move quickly. They're going to move on unstructured terrain because they just fly over it. They're not going to carry much payload, though. They're flying, and that takes a lot of power, and that's about all they can do at this point. You know, it'll get better, but really they're going to be power limited. An interesting thing about bees themselves, when they're in their natural habitat, they're going from point A, home, to point B, flowers that want to be found. So they have big colorful indicators and they're pretty obvious. And so the bee knows, I'm trying to go from here to here, and I don't really care about much in between, so I'm going to go straight shot, I'm going to do it fast. I'm not going to carry a lot with me or back, I'm just going to carry some nectar back, and sort of that's the whole scheme. And so that's a fantastic thing. You know, you can do mapping, you can do all sorts of things you could envision bees doing with robots. So that's really cool, but inherent in their physics, you're trading power for force. And so there's a couple integrals that are not helping you there. And you're not going to be very good at carrying large payloads because that's just not going to work. So they're fantastic, but they're not going to be able to affect the human world in meaningful ways. They're not going to move anything on this desk, for instance. And so we are specifically interested in robots that do affect the human world. So not only go and take sensor measurements from point A and point B and then bring them back, but take sensor measurements, record readings, make a logical decision on the fly, and decide to change the environment in response. So move a rock would be a simple example, something that's in the way. One goal would be even discover that the door to your room was open and close it. You know, sort of work in the human scale world. That's the goal. So we want to affect the human scale world. And ants are an interesting way to sort of be inspired there. They have incredibly strong ground motion, and that avoids that integral that flying sort of has to deal with, the power versus force. They trade work for force instead, so that's better. And they have really interesting team behavior. So there's a lot to say with ants. They're fantastic, really complicated species. Even though they're simple, they do a lot of really amazing things. So they're terrific, and they'll be our inspiration for this work. We're not the only ones. There's some other groups doing research more about the behaviors. There's other groups that are also doing kind of different kind of motions and things too, mechanics. So there's your 20,000 foot overview of microrobots as broken into 4 quadrants. And it really does cover a lot of them, believe it or not. So that's sort of where we are and where we're going. We're trying to make microrobots that not only measure things in the world, but affect the human scale world in response. All right, back to our outline here. So now we're going to talk about ways that humans increase force. So you have a nail and you want to drive it in. If you stood on that nail, you're probably not going to be able to drive it in. If you jumped, you might have a little bit better chance. But how do we drive in that nail? Well, we use a hammer, and that's a clever trick. It basically is able to integrate motion over distance, put it into the velocity of a mass, and then trade that in a short time duration to drive that nail in with an astronomical force. And so that's a clever trick we use all the time, even if we don't think about it. So that's neat. So using our own sort of intuition, it would be reasonable to design microrobots with this intuition. And in fact, there are many. So here's a sort of very simple schematic of such a microrobot. We have a magnet on a suspension. The magnet also has mass. And then there's a frame around there. And then if we change the magnetic field, can't do that very well. If we change the magnetic field like this, that mass will resonate, it'll start to get a large amplitude, and then it'll start to hit on the ground and kind of bounce. And that's a way that these things are able to move. They're able to apply, many times their body weight as instantaneous force as they strike, and they're able to sort of move smoothly that way, despite kind of being sticky when you get small. So again, we're able to get a large force achieved by changing that momentum quickly. So that's certainly a way that humans do interact with the world larger than themselves. So can we use this physics now to pull a load? So we have a proof mass here, and we have a little microrobot, and that microrobot wants to now drag this mass around. So that's the goal. It's not chance, the one I drew there. This is a toy available. It's called a Hexbug Nano. Here it is in slow motion. So it just kind of hops along the surface. It generates upward velocity, and then as it hits the ground, it trades that downward velocity now for a little spike in momentum, and it gets a little surge, and it's able to take more force out of the system than it could normally generate. So that's a pretty clever system. Feel free to interrupt at any point, by the way, if you have any questions or anything. So the physical assumptions of the system specifically are that on the average, in the long term, this robot is going to be limited by the mechanism propelling it. So if it's a friction-based robot, it's going to have a long-term time average limit of its body weight times mg and umg, sorry. But it is allowed to have impulsive spikes that are above this in the short term. So specifically, we're talking about a time average force that is no greater than the static friction affords it. And the max change in momentum in a stride is governed by these simple equations. But the main point is TP is the period of the stride, so that's the duration over which it's going to take a step, and it's accumulating that velocity. Here we see basically it's taking out that momentum in a short burst. So TP was the period of the stride. TC is the contact time of that force. So if it's an impulsive robot, it's going to be small. It's going to accumulate that momentum and then take it out in a small burst. And that gives you a force impact that's basically the ratio of TP over TC. So looking at that more geometrically, just for some intuition, here we have 4 different robot gates. We have robot D is a smooth running robot. So it's maybe walking or a driving car. It's just kind of smoothly moving, and it's applying a force almost all the time. So the colored portion is the time that's applying the force, and the white portion is the time that it's sort of recovering. So that's a pretty smooth moving robot. C might be a walking robot now, a little bit more jerky, but still pretty consistent. B, we're starting to see, most of the time now it's not spending or recovering. It's just applying a little bit of force, a lot of force in a short amount of time. I'm sorry. And then A here is sort of the limit, and that's sort of like if you took a hammer and you hit a string, you're going to increase your momentum until you take it all out in this one little burst. So what would their ground reaction forces look like? Here we have the long boring stride is generating its force almost the whole time. And then the shorter the time in which we take the force out, the larger the force we're able to get. So that's interesting, but just comes from some basic assumptions in physics. And you see there's different GRF curves here. So again, this is what these robots look like, just as a reminder. So we have these little hopping robots that sort of surge against their little string on the backside there. And if we measure the force in that string, this is what we'd get. We would have a series of sparse but large force spikes, and that is able to exceed the robot weight and also the level predicted by just μmg. So this is successful. This robot has achieved an interaction force with the world larger than its body weight, and that's doing great for it. So that's terrific. We basically are seeing a boost in the peak force capability of the robot. In this case, it's about 3 body weights, so that's pretty good. This is about 4 to 5 times what the coefficient of friction would predict. So this is robots punching above its weight, and that's fantastic. So now we're going to look at an example of how to use such systems to actually interact with a part of the human scale world. So this is a excellent little video that SRI let me show today. If you haven't seen, they're little micromagnet robotic platforms. They're pretty neat. Basically, it's magnets floating on a circuit board that has locally generated magnetic fields, and they follow those around. So it's low cost. They're able to move surprisingly quickly. They can even go up walls because there's interactive force. They can do interesting things like go on ribbons and different planes. You can use a lot of them together. Basically, the cost was in developing the circuit board, so you can just add more magnets to add more robots.
So the magnet is totally passive.
The robot itself is totally passive. That's right. The board is not. And you know, from a holistic view, the board is part of the robot. But so here we see 2 robots actually working together. This one is picking glue out of a glue reservoir and placing it on a substrate, and then it flips, and it's going to pick and place a carbon rod into that glue puddle. And then they're going to trade out, and the other one's going to do the same, and they're kind of doing teamwork here. Here's a robot picking and placing a vertical rod into an actively developing truss. Here's later research. You can tell the video quality is a little better. And they are doing a more detailed build cycle of a real truss now. So, you know, kind of feet scale, so definitely human scale. These robots themselves are maybe about 1 centimeter on a side, give or take, so they're pretty small. And don't weigh much at all. So here is the truss they're building. It goes out off the camera. The truss is moved by basically the equivalent of a crane. So something in the world is moving the truss larger than the robots can move. But then they assemble it at the sort of end as it sort of grows. And they're using an adhesive with ultraviolet cure so they can sort of cure on command. There's the structure. I've seen it. It's about this long. Haven't held it because it might break it. It's precious research. And here we see it's quite strong. So that was a kilogram sitting on top of this. This is definitely a human scale structure, and it's being built by Microrobots. So this is definitely our goal, and it looks like it's flying again. Sorry. Okay. So here we see the strength beats again. We've got a 1 kilogram weight on this little truss that these not very heavy robots built. Here's 200 grams in sort of a tricky mechanical situation that really wants to break at the base, and it's not, so that's great. So this is really exciting stuff. But we have to ask the question, these robots are not actively powered, so they're not super intelligent. We can add intelligence in the system with cameras or other sort of external sensors, but we want to be able to check their work, because presumably the goal here is to build large structures with hundreds of thousands of joints, and if you just rely on statistics to all be correct, that's not going to work. So what if, hypothetically, this joint right here was not functional? Well, this whole thing would crumble and it'd be a mild disaster. So we here at Stanford sort of were developing quality control for these robots. Now, one of the tricks here is these are human scale forces that they're applying, right? I have a 1 kilogram weight that this structure is fine with. And if I use these microrobots that are able to apply sub-gram, they can't really affect that much. They're so small compared to the strength of the structure that they're not going to be hugely appreciable. So it took some tricks to get this to work. So here we see one of the microrobots. This one is, I think, 3 millimeters on a side, so pretty tiny. And then this is one of the joints that they built. And basically the trick here is to do the momentum trick. So we're building up speed and then we crash into the structure, and that momentum is transferred to the structure quickly, and that excites its resonant frequencies. And then using this microphone that is very close to the camera, we can track those resonant frequencies and actually tell how much glue is in that joint to 1 part in 100. So that's pretty amazing sensitivity. And that's all thanks to this trick of trading momentum for force. So here we see, this isn't important, but we see 2 different resonant frequency sweeps. one without and one with the glue joint. So we're definitely discerning that capability, and that's great. So trading momentum for force is great. Let's go ahead and build a swarm right now. We're good to go. Well, there is a problem with this whole scenario. Maybe a couple, but we're going to talk about one today. So here is an easy to grasp demo. If you don't mind, bear with me here and we'll just go through this. So clapping is the same as impulse, right? I'm going to take my two hands, I'm going to accumulate velocity, and then I'm going to trade it out in an impact. So we're going to try to work as a microrobot team today, every one of us, and we're going to try all clap at exactly the same time. Exactly the same time. Not close, but exactly the same time. So on three, we're going to all clap. Ready? 1, 2, 3. Okay, that was, if you heard, not great. You all did fine, that's the expected result, but it's really hard to get these impulsive loads to happen at exactly the same time. And that was actually cheating. You were actually applying an internal force to the robot, and that's the easy thing. It's the external forces that are harder. So we're going to do this one more time, and it'll probably be worse. You're going to, if you have a neighbor, get to your nearest neighbor and do a joint high five. And we're going to try to all high five at the same time. So you don't know where the outside world is exactly, but you're going to take a best guess. So spend 5 seconds, figure out a nearby neighbor. Got your plans? All right. Thank you, guys. Okay, ready? 1, 2, 3. All right, so you heard that. That was a lot of disparate spikes, and they didn't overlap at all. And in fact, I did this in lab this morning, so this is a lab study. 5 of my lab mates, or 5 and I, got together and we did some claps. So we all clapped individually, and you can see the audio signal from those claps. Someone was more aggressive than others, but this is the set. And then we all tried to do a clap at the same time. And here's the actual result. It's maybe 20% larger than the biggest one, but statistically not different. And you see that where these are all sharp, over here that kind of builds, and that's the difference in the clap. So they're just not able to add very well. And the bottom line here is one that you should understand by now. Synchronization of impulse is hard. It's quite hard. The more impulsive you are, the harder it is to synchronize. So we're going to come back to this concept later, but that's sort of why we're going to need another concept. So, looking at that, let's think about adhesive robots. So we ask, how else can we generate large forces? Well, instead of using our intuition with hammers, let's think about nature. So here we have 2 examples of animals that are known for their strengths. Granted, they're different strengths. So we have an elephant, and he's pulling, I think it's a cart full of rocks or gravel over here. Big forces, they can certainly, not a problem to apply big forces to the world. And then over here we have a leaf cutter ant, cute little picture, but if we zoom out, we actually see that leaf cutter ant is easily being held by its buddy, and this is not even a problem for it at all. I don't think it even noticed. So ants are pretty amazing. Granted, they're smaller than elephants, so they can't move an elephant, but their relative strength is incredible. So let's think carefully about the elephant. Basically, elephants rely on friction, and friction is great when you're big. When you're an elephant, that's fantastic. And that's because the force you're able to generate, the friction force, scales as L to the third. So if you want more friction force, get bigger, simple, become an elephant, and you got this covered. But if you wanted to be small for some other reason, if you wanted to be a microrobot, then this clearly doesn't work, just at all. So we'll come back to this in a second, but it's a simple scaling law. We have an aluminum cube with a rubber base. As the cube gets bigger, the resistive force to pull it goes up, and here's just what that trend looks like. We're going to come back to this in a second. So now let's think about the case of our friends the ants. Well, adhesion is what they use, and that's fantastic when you're small. And this is specifically because the force of adhesion is proportional to the contact area of it, or L squared. So as you get smaller, adhesion is going to be the more useful force. As its scales decrease, L squared is going to be more helpful than L to the third. So here we're going to come back to that curve again. Now we see our friction curve. And we say, well, let's put a dry silicone adhesive on that same cube and just compare the relative strengths of these things. So interesting point, in this very simple system, it's a cube. Our crossover point is at 100 inches. So that says that we should probably be thinking about adhesives for anything that's even moderately small. That's quite a large crossover point. And secondly, in the size range where we'd start to consider them as microrobots, which is ironically about an inch cubed. It's not micro really, but that's what we call it. We see there's a 100x difference in the force capability. So adhesive is going to be incredibly attractive in this kind of size range. Okay, so that brings us to the next problem. Adhesion is great, but if you've ever played with duct tape before, you know it's slow. You put it down on the table and you have to work to get it off, and it's going to take effort. Hypothetically, if you wanted to move your car, you could put duct tape on your feet and you'd get a little bit more grip, and that'd be great, but you'd never run that way very well. You'd hit and be awkwardly stuck and probably trip. So adhesion is sort of problematic because it's usually slow. This becomes even more of a problem when you're a microrobot. If you're going to live in the human scale world and your leg length is tiny, that implies that that leg needs to recycle very quickly. So you really need to be even faster than we're used to, and so this is going to be a big problem. Adhesives are generally slow, if not even permanent sometimes, depending on your forceability to remove them. We would note that removability is a minimum requirement for use in a mobile robot. Otherwise, it's not very mobile. So here we have a chart. We have on this axis force, and we have time scale over here. And we see that friction is low force, relatively speaking, but is nice because it's available all the time, I suppose, but can be turned off and on. Controllable that relies on friction would be applying an active clamp to the object, then removing that clamp over and over. And that can really be controllable. So that's going to be able to be more useful. On the other axis, we have adhesive tape is bonded, so it's going to have more strength available, which is great, but then it's also kind of close to permanence. That's not fantastic. So what we really want here is a combination of can be turned off and on and has adhesive properties for strength. And we're going to call that controllable adhesion. So now let's look in detail about controllable adhesion. Before we start, have any of you heard about our controllable adhesives before, just out of curiosity? Or is this all kind of new to everybody? Got one or two little nods, okay. So those in the know, you're going to know what I'm talking about here. Those who aren't, that's great, we'll get through it. I'm going to introduce you right now to an incredibly useful force from nature, a force whose magnitude scales with size. It keeps things stable and from slipping. It can be turned on and off simply by removing the normal force. The normal and shear that it generates are temporally synced, which is incredibly useful because this enables dynamic motion, like walking or running. Also of use, it can be reused unlimited number of times, unlike that permanent tape. So that's fantastic. Those in the know, we're talking about controllable adhesion, right? Actually, this was just friction. And it's a really interesting point that we don't think about friction much because it just lives in our world and we just rely on it. I put all these things here on my desk, expecting them not to very slowly slide off if the desk wasn't super flat. And it's just sort of here, and we don't even really think about it, but it's incredibly useful in our lives, and we use it all the time. So I think this is a call out that friction is fantastic, and we should consider its use more often. But we're not interested in friction today, we're interested in adhesion. So let's look at maybe an alternative. So here is an ant, he's climbing up this stalk, and you can barely see if you look carefully, there's a little bit of discoloration at the feet. And that's because he's got an adhesive that's grabbing onto the stalk. This would be tricky with friction, maybe possible, but certainly tricky. But this is interesting because this ant has to move at a quick step rate, but yet is using adhesion. And that adhesion turns off and on quickly, and so here's how that actually works. Apologies for the crude diagram, but it's the best I had. So here's an ant leg right here, and he has a little hook on the end. And he's interacting with the world, which has some roughness perhaps or not, doesn't really matter a ton at that size scale. But basically, as the ant pulls on its leg, so the body is back this way, it's going to deform the hook, and then that's a mechanical object that it's just a lever system basically that spits out a little bit of adhesive. And so as that deformation continues, that adhesive is going to come out more and then find the substrate and become stuck. And now the ant's able to hang upside down because it's got adhesive engaged. But as soon as the ant goes the other way and starts to apply the inverse force or even just release the force, we'll see that the spring energy built up into the system is enough to peel the adhesive back off of the substrate and then kind of retract it back into the leg. And this is how they do that. They have a mechanism by which, as they engage and disengage their feet during a walk, the adhesive automatically is synced with the motion. And so they don't look like they're tripping because it just kind of automatically works out, so that works out great. They are slowed by a little bit by it, perhaps, but not enough to notice much, and they're able to do pretty amazing things. So that's ants, and they actually use a real sort of what we'd think of it as an adhesive, a sticky, gooey, adhesive that actually leaves a little patch on the ground. Well, there's an interesting animal that has some similar properties, but doesn't use quite the same physics. So this is a gecko up here, and they are known as basically the largest animal that uses adhesion to climb, and so they have a really complicated adhesive structure. So it spans levels. So here's the gecko. He's designed to climb. He has fingers that are designed specifically for climbing. If we zoom in on one of the little patches here, we'd see these rows of micro hairs. Here's one of these hairs is here. And then if we zoom in even further, we see here's a micron, and these are 10 nanometers across, so way smaller than a micron. And basically the idea here is each of these features is so fine that it conforms to the surface almost perfectly. And so despite not being actually sticky, it's just beta-keratin like your fingernails, it's going to be able to adhere to the surface and not leave behind any residue, which is convenient. So what it does is, as it applies a climbing force, the gecko is going to pull this way, and all the hairs are going to just kind of self-align onto that surface. Then it's going to be stuck to the surface by van der Waals force. And then mechanically, as soon as it removes that force, they're all going to just kind of naturally peel off. And this allows these geckos to actually run straight up a piece of glass at 15 steps per second. So they're really moving quickly. And that's really a fantastic inspiration for us. So we have developed an adhesive in our lab that mimics these kind of behaviors. So here's an optical microscope view of the adhesion being loaded onto a piece of glass that you can't really see in this shot. You see that the tips make contact first, and then just like the gecko, as we apply our shear force to engage onto that surface, we develop adhesion. And that's convenient because it's going to work like the gecko in the direction it wanted to go. So it's not wasting any energy, it's just pulling down. And unlike tape, it's not pressure sensitive, so it's actually shear sensitive. So we pull in shear and it turns on, and we remove the shear and it turns off. So it's a pretty interesting material that not many have experienced yet. If we look at its performance, we're going to see that it has directionality because the adhesives themselves are directional. They have features that go in a direction. So here we have two axes of stress. We have normal stress in this direction, so that's the ability to pull away from a surface. This would be adhesion below the zero line. And then we have shear stress, and that's the ability to sort of do what friction usually does for us. And so we see that this adhesive, when we pull in shear, is able to develop some pull-away force, so it locks onto the surface. And as we remove that force, it's going to go back to the origin where it's simply just removed. So that's pretty interesting. Here's the same setup, and we note that, so the trick here was we engage and we pull, and that lays over all the features, and that's terrific. But the other thing that happens that we didn't talk about is all these are little springs, and they're all deformed, and so there's energy contained within all the deformed springs. And so as soon as we let go of that force that turned on the adhesive, now the built-in spring energy is going to self-peel all of them. Since there's hundreds and hundreds of these features on any given patch, we're able to do peeling all in parallel, and that allows us to remove this adhesive very, very quickly. So that gives us dynamic performance, which is what that ant was going to need to do to run. So here we see that the release time constant was 0.01 seconds, so pretty fast. The other time constant of interest is how long it has to settle before it's locked on, and that's shown here basically. At low speeds, it's all fine. At 10 to the third kPa per second, we see that it starts to get a little bit upset. And so this corresponds to a reasonably sized robot walking at about 15 hertz. So pretty quick. Certainly fast enough to be useful. All right. So thank you for helping me wade through all those figures. Now let's do a little demo. Can I get a volunteer? Anyone want to come up and play with some adhesives? All right. I'll do it. Let me know if you change your mind. So here we have our little adhesive tile. So it's the same video shown there, but we have a rigid tile, and on the bottom, it's a little dirty, we have our adhesive. And if I set this down here on a moderately smooth surface, I can, if I just get it happy, there we go, I can now pull up to 14 pounds in shear for this little object. So that's quite a fair amount. But as soon as I pick up, you'll see almost with no force. I couldn't feel that actually. It just comes right off. So I'm able to turn it off and on with a lot of force, and then off again, and then on again. And I'm able to do that 15 times a second. That's fine. Someone ought to try this. It's pretty cool. Do you mind? Come on up. Great. So you're going to just pull in pure shear as best you can, like that.
Okay. Wow.
And then off. And you'll see, actually, as you pull in pure shear, if you do that again for me, and it's a little upset on this table. There it goes. I can actually pick up with a little bit of force. So I can hold about 10% of the weight that I'm applying in shear in the upward direction as well.
Oh, that's cool.
Yeah, isn't that fun?
Yeah.
And you can see, and I'll pass this around so you can see it if you like, but it's not sticky. So here's the material, and it's not sticky at all. It's just silicone rubber. And to a human, that's what it feels like, just rubber. But as soon as you put it on a surface that it's compatible with, it's locked. And so that's a pretty interesting material, one you probably haven't played with before yet. All right. Yeah. That's a great question in another talk. Basically, that was my first project here at Stanford, actually. We take a soft wax substrate, right now at least, and we take just a CNC mill, and we have a medical razor blade installed instead of a turning bit, and we carefully trace out trajectories with sort of maybe 5 micron level of accuracy, and kind of press that blade into the wax repeatedly, leaving little cavities that are the shapes that you saw earlier. And then we cast a liquid silicone rubber on it and come back in a couple minutes and we have our sample. So it is great for research. That doesn't scale well yet, so that's something that's sort of an active ongoing way to, crank this out more than handmade research. Yeah.
Is this material that you lost with the grooves in it?
What is the mold?
Yeah.
It's just a soft wax. So you can press your fingernail into it. And the wax is sort of low surface energy, so you can remove it later. That's one of the reasons we want it. It's also not very durable, and so that's only useful for 1 or 2 times, which means that process doesn't scale. So we're working on, a steel mold or something like that. Yeah?
You said that the Gecko structure was at the nanometer level,
Yes, it is.
and this is at micrometer level?
100 microns is the size of the feature. The smoothness is better than that. It's sort of micron level smoothness. The trick is the Gecko is actually using beta keratin like your fingernails, and that's really not sticky. You feel that, and it's specifically slippery. We're using material because engineering is at a state where it is. We can make these features. We're using silicone, which is more surface energy than beta keratin, and so we can get away with larger features and still get a similar effect. The downside is that the Gecko actually self-cleans, believe it or not. If it gets dirty, if it gets dust on it, after a few steps, it's less sticky than the environment usually is, and so it'll come right off on the trees or the leaves. Ours is not sticky to a human, and usually if you find a little bit of sand in there that's sort of fouled it a little bit, if you just touch it, it'll come off on your fingertips, but we're relatively sticky. We have oils and things on us, so it's certainly more sticky than the Gecko, and that's an area of ongoing research. It would be really cool to actually be able to make the Gecko adhesive. It's got some amazing properties, but right now that requires manufacturing on a scale that we're not capable of quite yet. Yeah, great question. Any others? More demos? Got some more cool stuff? All right. So we've basically showed a adhesive. It's clearly an adhesive, but it has properties kind of similar to friction if you want to think of it like that. At least functionally, that's sort of a good way to think about it. So that allows us to do relatively shocking things like this video. So this is my MacBook Air, this one actually, and I can do that. And it's not stuck at all. I can pick it up and put it down, but I can handle maybe 85 degrees to vertical, and it's fine. You can see the top actually starts to tilt away because of the moment induced, if you do the statics, but it's able to do that. So that's a pretty interesting capability if you're prone to dropping laptops, which I am. And I've actually been using that exact setup for the last year, and it's still on my laptop, same adhesive as original. I can't really move it out from the way here, but I can show you. It's a MacBook Air, so it weighs about 2 pounds. So, rubber you'd expect about 2 pounds of force. It's enough that I can move myself, and then I can still simply pick it up, and it's not even a hindrance. We have another demo video using bigger feet on the bottom that I'm able to pull myself to the desk like this using only a MacBook Air. So pretty interesting properties you've probably not encountered in normal life very often. So we've sort of talked about this material as an adhesive that's functionally more like friction. Well, that allows us to do something even more surprising. So if we put it as a thin film, like a tape, I can lift up an object with no effort, and then I can, under its own weight, simply drop the tape back off. And that's really strange. So please, someone come up and try this. I brought a demo, so maybe even a couple people. Yeah, great, come on. All right, so this takes a little bit of touch, but so this is made to go in this direction on this football, and that should work out pretty well. So go ahead and pick it up. You got it? This gripper was designed for that geometry. We can make more versatile ones, but this is a simple demo that's relatively bulletproof.
Cool.
Yeah, they're actually, the two different directions are opposed, so they tend to bite the surface like that.
It's the same material as the other one?
It is. It's just sort of on a
Bigger.
thin film now. Yeah, bigger. We don't need quite this size, but it makes it bulletproof for a demo. You know, I'm not actually watching. This is my PhD thesis, and I'm not even worried about it. So that says that it actually works pretty well.
Impressive.
So another cool trick you can do with it. So just flop it on there, and you can actually simply blow it off. It comes right off. So please, someone else. It's cool. You got to try it. Here, give it a shot. Okay. We've talked about that. It turns out they actually use an active adhesive. If you watch, they don't touch the ground because their fingers are actually sticky. So they're pretty cautious about that. So this is less sticky than they use, but there's no reason we can't make a formulation that's more sticky normally and then behaves more like less sticky under some conditions. So certainly an area of interest, yeah. And I thought I saw another question. We all good?
What's the manufacturing cost of this?
Assuming you scale.
Well, right now it's handmade by PhD students, so terrible. Yeah, that's fair. Won't be free as soon as I graduate, though. Then it'll cost them. Yeah, it's just silicone rubber, and it's cents. Yeah, silicone is more expensive than other plastics, but still we're talking cents, not dollars.
Millisense.
Yeah. I mean, if you're roll to roll and it's just sort of turning this out, they won't cost much at all.
Make it programmable, the direction?
Yes, the CNC mill process we can do.
Once it's this way,
Can you change
switch
it?
it on the voltage or whatever? Some controlling.
There are systems that do that. They often have other compromises, so I think your ideal would eventually be a hybrid, but we haven't figured out quite how to negotiate the ups and downs. Basically, to get more switching, we would lose some performance. Yeah, exactly. That makes sense. Yep. Yeah. Another one of interest is a slight flow outward to just kind of get a little bit of vacuum on the surface. That can help too.
Is it laminar flow? German, viscous?
Yeah, I don't know, something. Certainly it's a straw. What's that?
Did you write the thesis on it?
Not yet. Maybe later. So that was all interesting stuff. And I hope the demo is going around and you're enjoying it. Yeah, you got it. There we go. All right. Yeah, that's pretty much.
Kindergarten, the kids respond differently than adults.
They do actually. Yeah, it's interesting. We've given this demo a lot of times, and the children actually do better because they're more okay with physics that don't make sense. A lot of the adults.
No, they have to write physics per each program. You screwed them up.
I broke them forever. Yeah.
I'm thinking that something comparable to a tank tread, a loop of this that was dangled on something, would be able to pull it quite a bit and then release as the geometry brought something close.
Certainly that can happen, yeah.
So you could almost pick up a ball and cause the ball to spin as it dangled from this tractor tread.
You certainly might be able to. One of the tricks with the tractor tread is so we have almost no away force, right? It's basically all shear. And so the tractor tread sometimes doesn't want to stay on the surface because there's no incentive to do so. So it certainly can work, but getting those forces out are tricky. I think the best idea I've had is suction along that surface with a flat substrate or something to kind of keep it down. So there's certainly things one can do, but it's a little unintuitive and you've got to play with it a little bit. The tile that I showed you is actually one of the easiest low-hanging fruits to get a lot out of it, but clearly that film is bizarre and we're still getting our heads around exactly what to do with it.
Since it's shear forces, You know that sticky tape, the office tape, if you look at the microscale, it's actually microvorticity.
Oh, really?
Yeah.
Interesting.
No,
I didn't know that.
That's right.
Very cool. Very cool.
There's your thesis.
All right, got it. I already have my thesis, so I'm good. Another student. I just need to turn it in still.
No, it's actually worse because that makes vortices, and then when you rip it off, it actually produces X-rays.
Yeah.
People take down
I
messages.
knew about the X-rays.
To the X-ray film,
Uh-huh.
take down a message, and then it was exposed. And
That's so
you have
cool.
to figure out why was it exposed.
That's cool. It's a
And
lot
it
of
was
fun.
microvorticity.
Yeah, that's really neat.
It's viscosity. It's basically very viscous. It's actually at the
Sure.
microscale viscosity.
Makes sense.
Vorticity.
That's very cool. So clearly we have a material here. This is a simple demo to get in your head, and that was the point. You know, it's pretty sparse. There's a thread and a stick and a piece of tape, and that's about it. Well, what happens if we try to build this material level intelligence into a more complicated system? So here is a barely more complicated system. So here we have a series of these tapes and some airbags behind them, basically. And this is all compressed with a spring only. So this is, you can see that poof ball. I'll do that one more time. Demonstrates how much force this is. It's basically nothing. Just enough to kind of engage them on the surface. That's a very squishy object, so that should be deforming if there's any force. And it's not servoed at all. It's set by a spring at some point in the system, and that's all that we get. And we can see that this probably $2 robotic hand, I mean, I'm robot in quotes, there's nothing fancy here at all, is able to pick up a huge variety of objects with almost no intelligence. So sacks of things, potato chips, bigger objects.
So those quadcopters will have that?
Yeah, we've certainly done some of that. We have quadcopters actually that can perch on walls and ceilings, and you know, release is the important part. You can always put duct tape on a quadcopter; it would stick to things, but releasing is the hard part. So really interesting material with some clearly interesting properties.
By heating it up or some other electrical magnetic heat?
With duct tape, you mean?
No. Well,
We don't need that.
There are
It
various
comes
ways
off.
to get symmetry breaking.
Sure. Including just remove force.
Magnetic fields is
Sure.
one way to do it.
Sure,
Yeah, but
that would
also
work.
but it could be electric field magnetic.
Yeah, usually we just remove the weight, which is an asymmetry
Yes.
break as well, and that's enough to do that. And if you are able to get on a ceiling, you're probably able to remove your weight. That sort of comes with the territory usually. So yeah, this is really interesting. I think, yeah, this is a cool shot. So this is a box for picking up. That's easy, of course. But we're going to do it the hard way, which is actually hard for a human. Yeah, and that works fine. So basically, in the end of the day here, we have demonstrated an adhesive that you can think of like friction with a coefficient of friction in most reasonable situations of like hundreds. So a pretty bizarre thing that we're not used to dealing with very much. Great. So it is strong like a standard adhesive, and it is fast and controllable like friction, but this is going to have a cost. Everything has a cost, so that's not a huge surprise. If we look at the wedges, we're in this state before we apply a force. We apply a force, we get a displacement. That means work. So in the loaded state, we've added work to the system. Now, as a human, it's not enough work to notice. You know, as you're playing with that football, you didn't notice that it was deforming just a little bit. It doesn't matter. But if we start to become ant scale, all of a sudden that work is going to start to add up. And so that's going to be something that'll be a core thing we're going to have to deal with in microrobots. All right, any other questions before we move on from adhesive? There'll be more of it, but yeah, and we can talk more after.
Have you looked at microscale? What's happening?
It's van der Waals force. Is that what you mean? Or? Yeah, no, that was pretty clear.
All right.
So now we're going to build a series of robots that demonstrate the various unique properties of this adhesive. So let's say I wanted to make a small object that influences the world. As an engineer, I need engineering ideas, maybe not nature ideas quite so much sometimes. So I'm using a tugboat as an inspiration here as an engineer. We have a tugboat consists of fuel, a lot of it, a giant engine and a giant propeller, and then the humans up here are just basically accessories, so not much else. Just engine, propeller, and fuel.
I can. Got it.
Here, I got it.
Here's the road.
All right. So let's make a robot equivalent of this tugboat. we're going to see that we have a lot of fuel, or in this case a LiPo, so it's about 30% of the volume up there. We're going to have the engine becomes incredibly important. If we want a small robot that can exert a large force, there's two problems. One is the ground reaction force, and that's the equivalent of the propeller. And that's a problem, but we have this adhesive that's cool. And now the engineering challenge is just getting enough actuator in this volume to accomplish the necessary goal. And so that'll be a large actuator. So we're going to use these robots to demonstrate 4 different properties of the adhesives, specifically the speed, full use of the adhesive force, the efficiency of a system using these adhesives in this way, and then the light touch of engagement we're able to see. When I was using the football, I could just throw it on there and not press it down, and that's a pretty handy feature. All right, so this is a force displacement curve. So for those of you who aren't physicists or mechanical engineers, we have displacement in this direction, and we have the force required to get there, basically pressure, but same thing. And if we integrate anything in this curve, we will see joules per meter squared. So basically it's the work that the system has to do to achieve these points. So as discussed, the adhesives at 0 force are under 0 displacement. That's as expected. And then as we increase the force little by little, we're going to increase the displacement out to here. For the adhesives to be performing at peak capability, we're seeing about 7 joules per meter squared and this star point here. So that's a really important point. In order to use this system at its best, you ought to be operating at the star point or not further because you'll fail. But the star point is the goal. So microrobots have one unique and tricky challenge, and that's actuators. There are not many great actuators once you get small enough. Motors start to peter out at about this sort of 1-inch size scale. And then we're left with solid-state actuators, which are fantastic for some applications. So we have piezoelectrics, electroactive polymers, shape memory alloy wire, all pretty useful materials in a lot of applications. But we'll see that the cycle work for piezoelectrics, they're very fast, so the power is reasonable, but the work per stroke is quite minuscule. So if we were to use PZT for our only actuator to develop this only this amount of effort, the peak work we're talking about for a 1 cubic inch robot, we would be taking over 50% of our total volume with simply the bulk PZT, no transmission, no battery, no power supply, nothing else. It's just half PZT. And that is completely unacceptable to make this actually happen. Electroactive polymers are going to be better. They have a factor of 20 more work per cycle. So that's great. That means they're down to 2.4%, which is totally reasonable for an engineer. However, they also require a 1 kilovolt power supply, which is, again, unreasonable. So there's all these challenges with dealing with these solid-state adhesives. We will note that gears, if you can get them small enough, don't have a work cycle. They keep rotating forever, and that makes them ideal if you're able to use them. And so we're going to use some of that sometimes, but we'll also demonstrate use with the more hard-to-use materials as well to show that it's possible. So, looking at that now, we're going to talk about adhesive speed. So the first two in that table were PZT and electroactive polymers, and this is their force displacement curve as actuators. There's a variety of reasons it's a different shape, but this is sort of typical in this kind of actuator. And so to achieve this point, we need to have that on this line, and that means that our actuators are going to have to do this slope to achieve that point. That's just some basic geometry. Because this is their slope and not matching what we actually wanted, that means we're going to waste 4 times the work cycle that was already hard to do because of this poor shape match, and that's problematic. So that means that they're going to be requiring 28 joules per meter squared instead of 7, much worse. However, they are very fast, and that's where we're going to use them to demonstrate the adhesive speed. So we have built this very simple robot. It's almost comical how simple it is. And therefore it's hard to understand, as always. So here we have a schematic showing how it works. It's basically 4 legs moving with 2 bending elements. So I have, the function of this is basically that I'm going to flop on the ground kind of like a fish. I'm just going to do this over and over, and I'll raise up my belly and then drop down, and raise up my arms and then keep cycling through. And with PZT, you don't get much displacement, so you won't be able to see that very well, but if you look carefully, you can, and I'll show you where to look. So here is our actual little robot. We have a dummy proof mass because it was easier to run power off board for now. But we have these 2 bending actuators and then the adhesive feet. And then the payload, which is about 10 body weights, which is not incredible yet, but it's certainly more than nothing. The adhesives have about 2 centimeters squared, so we'll need about 0.005 joules. This system is able to develop about a 20th of that, so this is really not demonstrating the force yet. It's just showing that they are capable of being fast. So, without further ado, here is our first microtug robot. So you see the motion there if you look carefully. This is operating at 16 hertz now, and at 16 hertz it's fast enough it just kind of seems like it's gliding. And there, I'll do that one more time so you can just, now that you know what you're looking at, there's the little walk, there's the faster walk, and here's the glide towing about 10 body weights.
What's the fastest frequency you can run?
That's an interesting question because it depends on the amount of load. The more I load it, the deeper into that cycle I get, the more stuck I am. With light load, so the 5 grams of its body weight, I was able to run easily at 64 hertz. For pulling 10 body weights behind it, I had to slow it down. 16 was
Is the curve proportional to what? Quadratic?
Complicated.
Do you
Yeah,
have a minimum?
a minimum of speed, a minimum of time.
Is it a convex concave curve?
Ah.
Saddle point.
We didn't check very carefully all the different parameters. The adhesive itself is pretty nonlinear because you're getting increasing patches as you displace. It's monotonic, yes, but it's not just a simple quadratic or a line for sure. So off the top of my head, I'm not sure. I can sort of carefully think about that, but not while I'm giving a live talk.
It's a homework problem.
All right, thanks. I'm almost done. Yeah.
If a pile of nuts was on wheels or grease, it'd move easier.
It certainly would. So this is steel on glass, and you bring up a very good point. The research topic is dragging. Let's be clear about that. And dragging is always confounded by friction. So just get that out there. It's absolutely true. We tried not to cheat very much. You know, steel on glass is a relatively common thing. I'm not using Teflon. I'm not using grease. Steel on glass was this, and that's the performance. But it certainly is very much true. We're not trying to overclaim. We're trying to say that in a realistic scenario, this is what it can do. Later, we will overclaim a little bit, but try not to overclaim too much.
Wait until you go out for financing on that.
Yeah. I mean, it's just inherently true that it's always going to depend on friction, this topic. It doesn't mean that you can't still appreciate as a human that if I did that, that would be hard. But there's always going to be that confounding variable that's friction. You know, a lot of the comments I get is, well, just float it on a boat and you can do infinite weight. I'm like, well, yeah, but that's not useful. Anyway, so here is, again, demonstrating speed with piezoelectric actuators. They've got a ways to go before they can get the work out of the system, but we can handle the speed when they get there. So that's great.
What's the efficiency of this? How much electric power?
Oh, it's pretty bad. I wasn't trying to optimize for efficiency at all. So
Point is again, like if it's inside the physics.
yeah, PZT is pretty efficient. It's probably 80% overall. The problem is, and we'll get to that actually in the third section. So there's an important part to make about efficiency in such a system. So we'll get to that. But yeah, it's not very efficient as is. The actuator itself is pretty good, but the system is wasting a lot of power.
Typically, if it's not efficient, you don't understand the physics.
Well, I understand some of the physics, but the PZT.
That's a bad joke.
Yeah, okay. It's tricky. The PZT is not very capable, and we have to push it to its limits to get it to work at all. Okay, so having talked about PZT, which didn't have a ton of work, we're going to now look at something that has more work available, and so we're going to be able to actually use the full force of the adhesives. So, here we are. As a reminder, here's our controllable adhesive work. Here's the point we need to achieve. Here was the PZT and electroactive polymer curves, so poor shape match, factor of 4 more than we needed. Now, shape memory alloy is an interesting material because it's got a curve that's basically flat. And so that's really interesting. It's clearly a better shape match for what we're trying to achieve. And so with shape memory alloy, we only need 14 joules per meter squared, which is much better. But even more importantly, shape memory alloy, in addition, has an extra 200 times the work per volume of PZT. So all of a sudden, now we're talking. This is a functional system. Again, there's also a 2x less work required, so we're talking 400 times better than the PZT robots. And this is going to be enough work to fully, really use the adhesives, which is fantastic. So here is our robot schematic. This is what you'll see in a video in a second. Basically, we have 2 feet, an outer foot and an inner foot, and they have a spring in between them. And then a tail is attached to 2 pieces of SMA wire. The wire is going to contract when it gets hot and pull the one foot with respect to the other, and the result is an inchworm gate that kind of just moves like that. So the main portion, the functional portion here is about 4 grams. Assembled with batteries and everything else, it's about 12. And it's functional. We actually pulled our most famous lab member, Sticky Bot, up a wall with this object, but the efficiency was just absolutely beyond terrible. It was so bad, it's ridiculous, so we don't do much with it. But here it is in use. This is just the body, so this is about 4 grams. And if I hit play, we're going to see this 4-gram robot moving a 2.5 kilogram steel on glass load. There it's this little inchworm gate, and there we're moving the load. So that's certainly getting interesting all of a sudden.
Now you're just showing off.
Not yet.
They seem to be asymmetry. One is pulling, one of them pulling more than the other. Is it like walking?
So there's some complicated.
Or is it asymmetric?
The left, right, or front, back?
Well, that's part of the question. The wire closer does seem to be doing more work than.
If that's true, it's accidental. It's hard to build these things by hand, but
ideally you want it symmetric or not.
if you're not turning, yeah, that would be the goal.
So it is a walking wire or crawling wire.
It's taking its full front and putting it down, and then its full back. So it's
symmetric.
yeah, it's supposed to be symmetric, and then it varies.
Because that's engaged. It's interesting. The symmetric modes versus anti-symmetric.
Yeah,
versus
that is
combined.
Certainly,
Or even circular, like they all might have different efficiencies.
they certainly would, and that would allow you to do things like turn left and right. For this example, we're really only focused on can a microrobot pull a large thing, and the answer here is yes.
Symmetries of the physics are.
Yeah, it's interesting.
Inchworm model.
Yeah, it's an inchworm. That's right. With some complexities because these are all tendons driving it, so there's a lot of it we could talk about later. But it's and some of it I've forgotten because it's been a while. But it's a complicated thing to make it work. It certainly works, and it relies on the properties of the adhesives to kind of get some of those things to work. All right, so that's neat. Now let's talk about actual efficiency, and this is sort of where we're going to see some problems. Okay, so again we have our adhesive required work to turn on. We have our PZT curve up here. And remember, the PZT was hard to do, so we're not really even achieving this point probably. We're a little bit down below it, but that would be ideal. And then we have SMA. Well, this was the work required to turn on the adhesives. And at that point, we've actually accomplished nothing. The adhesives is on, and that's it. We haven't done any external work. So in that case, our efficiency is 0. It did turn on the adhesives, which is helpful, but the efficiency still hasn't come into play. It's 0. So this is very interesting because if we extend SMA out a little bit, that's more realistic of what you'd have to do. You have to get something after you've achieved that point. And we see now, motors are able to just continually cycle, and so now all of a sudden we can get efficiency out of the system. And that's very helpful. So if we used SMA, again, as noted, if we only stop here, we've achieved an efficiency of 0 in that cycle. If we go out to 125 microns instead of 100, now we're up to 33%. Even at 200 microns, we are only at 0.66 still. So, it takes a while to accumulate functional work out of this system. So really, we want the actuator to be as long as possible. And again, a motor is going to allow us to do that. So here is our motor-based microtug. We are loading the adhesives and any other springs in each cycle represents a fixed loss. So if I have an extra spring, that's a more loss, but we know at least the adhesives will be a loss. At infinite step size, the efficiency, that doesn't matter anymore because now we're just limited by our actuator's work efficiency to put out work. And winches allow for near arbitrary step size independent of the robot. So I can make a 1 cubic inch robot that has a winch that pulls for 6 inches, and that would be sort of ridiculous if that was its actual walking distance. That doesn't work. So winches are incredibly attractive from an efficiency standpoint. Small DC motors have efficiency on the order of 10 to 20%. Interestingly, they're limited by their bearings usually. The torque output of the motor as you get that small becomes diminishingly small, small enough that the tiny little jewel bearings they're using in the high-end ones become a fixed percentage of that torque that's a lot of it. And so you start to lose efficiency.
What interesting is if you keep the force below a certain very weak amount, the friction goes to 0. It's like a superconducting effect.
Interesting.
You may want to look at that.
Yeah, that's interesting.
At least the Swiss watch industry discovered that.
Interesting. That's cute. I like that. Anyway, so we're seeing about 20% efficiency. The shape memory alloy from the previous robot was able to achieve the work, which is great, but its sort of theoretical max for most alloys is on the order of 2%. And in our practical application where we're using it poorly in a microrobot without much control, we're way lower than that, factors of 10 at least. So this means that our batteries can be dramatically smaller, and as we saw, the batteries are a non-negligible part of the volume, and so that's going to be incredibly helpful. So here is an explosion view of the actual robot. So at the bottom, we've got our tile, as we all saw, and it has tendons sort of running around it as a pulley going back to a hook, and then a little outlet here. And then that string is attached to the output of a winch. It's a micro servo, basically, that's been hacked. On the output shaft there, we also attach this series of motors and wheels that is able to lift and lower as the clutch moves. So it's just a friction clutch between here and the winch and spool. That represents a loss because you always have friction moving there, but it is able to get a lot of degrees of freedom per cubic inch, which is hard. Then we have a sensor to sense how far the winch has been moving, because a lot of the systems are going to be close to stalled, and so the time can be a poor measure of what you're doing. And then we have processor, motor drivers, and batteries on top. And putting that all together, we have our first really functional engineering device. So here he is, little 12-gram robot. He can drive forward, turn, and then raise and lower his belly. And you'll see that the adhesives on the bottom aren't even slowing it down. Yeah, he's able to go quite fast. But then when he wants, he can lower his belly on the ground and now winch that coffee cup all over the place. He's got that coffee cup like crazy. Coffee cup was about 50 body weights, if I'm not mistaken. It was full. Here's a comparable weight and sized robot, clearly not accomplishing much because it's just friction. But here's 350 body weights. This is 9 pounds. I gave up finding weights in lab, clearly. And there he's able to do his little gait. Does that make sense? Any questions? Good time for it. And now we're going to test the limits of engineering here. The adhesive can do about twice this. This is about 50 pounds, so about 2,000 body weights or so. And the main limit is actually the motor. The adhesives are fine to do more, but the motor wants to explode, so yeah. So that's about what we can achieve without sort of stepping up, and we do step up later. But
electrostatic
there is just very hard to get a combination of drivers and actuators together in a cubic inch. If you give yourself a little more space, then absolutely. But we kind of had, there's a classification of robot called nanosumos.
There's no information.
I mean, you could, but there's no commercial ones available, and the research isn't make things. But
that's what your muscles do.
Yeah, it is. That's right.
You should be able to do that too.
Yeah.
Thank goodness you're doing this work in the U.S. where you're on the inch system, because a cubic centimeter.
So believe it or not, the standard actually I think came from Japan. I don't know why, but they have these nanosumo robots that have fights, and the goal is to push each other around. And so the joke is we won that competition. We didn't actually. I don't want to enter, but you certainly could do quite well. Okay, so I got to move forward a little bit. Yeah, that's right. So we have robot efficiency here. So we see as the step size increases, the efficiency goes up as expected. However, our corner position here basically is on the order of millimeters. So this is dominated by extra springs in the system that are unaccounted for by the adhesives. It's the same effect. It's all going to be the same effect. And that tells you that if you make your system stiffer, you'll get better efficiency per stroke. Or if you increase your step size to be ridiculous, then none of that matters anyway. It's still a loss, but it doesn't really functionally matter. Great. Here's the ground reaction forces we measure. Red is shear. Clearly we have a ton of shear capabilities. Interestingly, blue is the normal force. So here we see the robot driving onto the platform, and here's his weight difference from the start there. So that's the robot weight. And then during the pull cycle, he actually develops 50 body weights away from the surface because it really is an adhesive. We're thinking about like friction, but it is an adhesive. So he's developing 50 body weights upwards while doing this sort of ridiculous maneuver here. So that's pretty exciting. There's a lot more videos, but I've got to actually move along. We're running out of time. And okay. So there's lots on our YouTube channel. You can find them all. That was for the BBC Kids show, so it was a little bit less formal. It's cute. So now light touch of engagement. I'm going to kind of fly through this, but the trick is that it doesn't require much pressing. You know, some tapes you really want to push down and mash down, but if you're climbing, that's going to be hard, because if I have to press down with my upper hand, that means I'm pushing my body away with the lower hand, and that's problematic. So we've built a little robot to demonstrate climbing. Here's a measurement of the almost zero force of engagement compared to the loads that it's able to take when it actually takes the step. And I'll show you a little video of it climbing. So this is 110 body weights payload, so 5 pounds or something like that. And that's how it takes its little step. And you see that it doesn't require any push-in force at all. It's just skittering on the surface barely to turn on. But as soon as the shear happens, now it's locked. So that's a cute little robot that's able to climb with a 100 body weight payload. That's neat.
Now the shaky the robot.
So, yeah, we can actually, yes, it was certainly 90 degrees. I think we had one that did a little bit more, just for fun. But that's a little bit harder. So takeaways here, we've shown that the adhesive has speed, it has a work of engagement, it has a step efficiency, and a light touch of engagement. So these are all the properties you need to consider when using these for microrobots. Careful consideration of these properties and actuator selections allows you to make a robot that's able to move a 50-pound weight on glass. And that's pretty surprising. So if we look where this stands compared to existing state-of-the-art, which of course they weren't trying to pull things, so but this is just sort of as a comparison. We have microrobots that are frictional and don't have much weight are here. So length and weight are correlated basically. This is what you'd kind of expect if you were just predicting an average weight. Climbing robots do a bit better because they always are adhesive. They have to be to climb. That sort of comes with the territory. But they're right here. Here's our microtug body weight. So if it had a coefficient of 1 frictional material, that would be the red dashed line. And we see if we add our microtug to this curve, wait for it, there. So we're clearly a bit of an outlier. And this is able to actually affect the human scale world. So that's pretty exciting.
Speaking of climbing, does it work on a smooth granite surface?
Yep.
I know you're going to Yosemite.
That's right.
That's not smooth.
That's not smooth.
We have other materials that work on
You have
that
to
too.
smooth it ahead of
That's right, grind it. All right, so we've got not a ton of time, so I'm going to try to get through these last couple slides. So now the question is, we've developed robots that are individually able to have a lot of force. And you recall the other way we did that engineering-wise was with the impulse, which was sort of problematic. So we're going to go through exactly why that is. But now that we have more ant-like things, can they actually share load like ants? So this is a picture of, I don't know, maybe 8 ants moving an object that's not huge, but they're clearly working together to do it, which is great. And now for the cool thing. This is a video that Stefan de Graaf allowed me to use. So here we have, isn't this incredible? This millipede actually goes out like here, it's huge. And we actually see teams of ants, sorry, locking onto each other to apply load sharing to the system when the perimeter runs out. They're all on the perimeter, that's a granite, but once the perimeter runs out, they're actually biting onto each other and sharing load. So this is incredible capability from these ants, it's really neat. So the question is, can we use teams of microrobots to do the same thing? So now instead of one robot, we have N. What would we get if we did these impulsive ones, what we saw before? Well, one impulsive robot has a peak force of about 15 grams. 20 impulsive robots has a peak force of about 30 grams. So they're basically not doing anything together at all. It moves faster because we've added more power to the system, but they're not any extra capability really at all. Again, that's just because if you look at the sparse curve from one and you put another random one on top of it, they never add. Just like our clapping never really added.
If you had really good synchronization, though, they could, right?
They can, and it's just hard. And we actually tried that. We seismically excited the whole system so that should be pretty consistent. And it turns out that these robots are so impulsive, the error that causes a complete mismatch of those signals is only 500 microns difference in height. And given that they're toys, they never were able to synchronize that well. And believe it or not, in such a system, it made it worse because it introduces systematic errors instead of just random ones. So certainly that's possible if you can do it, and it's just an engineering challenge, but it would require at minimum good communication. And hopefully knowledge of the environment too, because these impulses happen short time as well as short displacement. So you need to know exactly when you're going to hit to synchronize very well.
Those work in muscles. There's a story that mothers have been able to get the kids from underneath the car. A single mother lifting a car by really focusing.
Yeah.
I've never heard the details of that story. I know about the story.
Clearly, we need to experiment with all the cars on kids.
Done. All right. So this is, I really have to fly because we're basically out of time. But this is a statistical model. It's just a binomial distribution with some modifications to make it work for this particular scenario. But basically we're saying that If your contact patches are wider, you're more likely to add. And if they're narrower, they'll be more force individually, but they won't add as well. So here we see a cute little video of 20 robots being wrangled on my desk, and they basically don't accomplish much. So here is the force per robot. As we increase the number of robots, it just basically plateaus, doesn't do anything useful. And here's the actual slope. So in some cases, if you do it well, you're getting 3 times or something. I can't quite tell from this angle. The force out of 20 robots, it's still quite poor. How would you improve this? You're going to improve the time in which they're generating the force. Is it better with synchronization? It's a great question. It can be. So here's synchronization. You're just going to sort of effectively reduce the stroke length mathematically. But the problem is that has the possibility for systematic error like this and can cause worse problems. It sort of just depends how good your synchronization is and how specific the case is. Interestingly, we can actually take walking robots and convert them into running robots by driving more power into them functionally. And we actually see that if you're trying to do one robot, you're better running because you're going to have some of these surge effects. And the walking one's right there. But even after 5 robots, the walking ones actually start to exceed the capabilities of the running ones. So this is a very real effect that happens. So how would we achieve ideal load sharing? Well, we'd make it all green, basically. What have we showed before? Very slow robots that are operating over a long time and a long distance. So this is going to be totally perfect for our microtug robots. Here's their effective gait. It's just very boring. It's flat. And in fact, if we take 6 robots, we get linearly 6 times the force, allowing us to not lose anything. So this is maybe the assumed result if you weren't thinking very carefully of this system, but it's basically as good as you're going to get. And that allows this team of 6 to do, I think, about 84 pounds of peak force, which is interesting because our lightest lab mate, who was on the paper, can only apply about 87 pounds of force. So we almost beat one of our authors. Here's a test showing that not super important. Here is one of the new version of the winching robots, so better gearbox, stiffer, more efficient, all those things we talked about wanting. And there's a 50-pound weight. Now it's able to easily pull it. The other one is struggling. Here's 7 of them kind of being tested at the same time. And then we take 6 of those, the best ones, because one broke. And here is 6 of them at 20 times speed, pulling my actual daily commute vehicle. So now we are cheating a bit. We're using a car, but clearly this is a force large enough that children couldn't do it. And that's the goal. It's just give something humans understand, something that they might have seen but know that it's difficult. And so there we are, pulling a car. So again, if we look at the microrobots from friction-based and climbing, and then we add 1 microtug, it's there. And now we've scaled without any loss, which is always hard to do in the real world. And so if we look at that team as a single robot with some modifications mathematically, it would show up about there, which is now clearly getting a bit ridiculous. And so we have truly shown ant-like capabilities. We're affecting the human scale world with small robots, and that's pretty exciting. I won't go much into the takeaways. Takeaway is what you saw. It's pretty neat. Here, I think there's a great video you should watch on our YouTube channel, narrated lovely and stuff. A little more for human consumption than a research talk. So the last point to make here is, okay, so we've shown swarms actually working now. We have 7 robots mechanically working together. That's great. So can we use this to do things in the real world? How about building big structures? Well, ants, if we look at our example again, are able to build gigantic structures. They're incredibly cool. So that's clearly possible for ants. However, the thing to note is that basically ants are building incredibly complicated but not specific structures. And that's a difference. So for swarm mechanics, it's a lot easier to say, here's your motivations, just figure it out. But as engineers in the human world, we almost always want specific things. And that makes swarm research tricky. So we have a paper about this recently that's just pointing out that it's tricky. No solutions yet. But basically the idea is with a specific structure, we're almost always implying a top-down result, and integrating that into swarm mechanics becomes problematic. More research is necessary, and it's exciting to see when it figures out, but it's not obvious exactly the ways to make those work. All right, thank you for coming to the talk. Thank you to the co-authors, and thank you, everyone.
Was it part of the cheating to put your tires up to 50 pounds?
They were at their maximum rated level. Yes.
Maximum rated.
On the tires. It was tuned up.
The 50.
Yeah. It was whatever these tires are specifically. I don't remember.
I have the same.
Oh, you have the same car. Okay, so 50. Yes, I'll take your word for it.
50.
50. Got it.
So
about 26 years old.
Uh-huh.
This is electrical engineering. Huh? Yeah, it's Trey's comment. He said, well, what do you want to plow a field? Do you want 2 strong oxen or 1024 chickens? And,
great.
you know, unfortunately, he died.
That's a great quote.
I heard it as, 2,000 bunny rabbits, which is more of an impulsive thing.
But when you can't make oxen big enough, which is the problem we ran
Also,
into.
both are hard to synchronize.
So we actually have a Roomba-sized robot too that I didn't talk about that can move 200 pounds in shear, so enough to move about 2,000 pounds on a smooth surface without cheating. Pretty
Well, I think
shocking
the interesting
object.
thing with your demo football there is the fact that a quarter of it is not a smooth surface on the wide side.
Yes.
It's not effective on the...
This was designed specifically
Right.
for that. We can do the other, but both is hard at this point.
Yeah.
That's right.
Thank you.